So we've been working a lot with modeling projectiles, and it seems to match with experience, right? We seem to have this general idea that things travel in an arc, that arc is going to be impacted by drag. But how do you know if a computational model is actually working? How do we know if all this update stuff and these forces we've attached to the projectile are actually producing the type of motion we see in the real world? For that, we would need to take some measurements. And it's actually very hard to take measurements of a thing flying through the air, right? I can measure the distance. I can measure the height if I'm clever enough, and I can definitely measure the time. But I wouldn't be able to measure the actual trajectory. That is what Tracker is for. Tracker is some free software available on compadre.org that will take any video that you take and allow you to track the motion of different items in the video. I'm working with the installed version of Tracker, but they recently released an in-browser version. So if you're working off of a school computer that you don't have installation rights to, you can use the online in-browser version of Tracker to do experiments just like this. This is a basketball toss recorded at Eubank Elementary School. Go and check them out on YouTube. And we're going to use this video to track the motion of the basketball as it flies through the air. So in order to do that, I need to go up here and create a point mass. We're going to call this point mass the basketball. And so now whenever I want to reference that basketball, I just go to the menu here and I select the basketball. Now, in order to do the tracking, I need to do this manually. You can sometimes get it to automatically track. What I'm going to do is hit Shift click wherever, let's go with the center of the basketball is. And you'll notice that it advances forward 1 frame here. Whenever I hit Shift click, it's going to move me forward in the video each time I do Shift click. And so it's just going to take me a minute here to do a bunch of shift clicking. So let's go and put this in fast motion. Now you might notice I've had to double click on a lot of these, so you can see in the graph where the data sort of plateaus out here. That's just there are 2 identical frames in a row there, so I was recording this at a frame rate twice as much as the video was moving forward on my screen. That's okay. We can work around that. That just tells us that half of our velocity data is not going to be useful, and that's okay. Let's see what we can do here now. So now when I go to play this, if you watch, you'll see that the dots follow along with the basketball there, which is pretty cool. And you can see I get a pretty good parabola there. If I were to do y versus x, I might get a pretty good parabola. That's pretty decent. There's the bounce back. Now, what I want you to notice, though, is that the camera is moving, right? So we have to account for the fact that the camera is moving along with the video. In order to do that, we have to set up a reference frame. What that's going to involve is finding an object in the video that I can kind of track as well and say, pretend that this dot is stationary. This will make sense in a second. Let's find a spot on the video. I'm thinking something on this drapery here might work. Let's see, we've got the toss here. We go up to the basket. Okay, yes, I think that something on the drapery there is going to be the best because that stays in the view the entire time. Okay, we're going to take, see this little black dot right here? We're going to take that as our reference point. So I'm going to make a new point mass. We're going to name this one reference point. And all I need to do now is activate reference point here, and I'm going to shift click everywhere that reference point is. And we'll go back in fast motion. Perfect. Okay, so now what I'm going to do, let's go back to the beginning. We're going to draw in our coordinate system here. And I see that I'm a little bit crooked compared with the floor, so we're going to make our coordinate system look like this. So this will be the x-axis, this will be the y-axis. And what I can do now is go into coordinate system and tell it that my reference frame needs to be the reference point. So what that's going to do is it's going to lock the reference frame here at reference point. And when I click play now, what I want you to notice is that the reference frame moves along with the reference point. See how those axes are moving on the screen? Now I have a nice consistent point to measure from. And I actually clicked pretty well there. It's within, 10 to the minus 13 of each other there. So I think we're in pretty good shape there. Now if I go back to my y versus x, let's go back to mass A. Now I get a better idea of what that parabola looked like. There's another way you can explore this, and that's to go into the what's called the world view down here. This is where it takes into account the motion of the camera. Let me show you what this means. So up here is the original video. Down here is the video adjusted for that reference frame. So if you notice, the frame of the video itself moves along so that this stays in position. So if you were sitting there on the sidelines, this bottom view is what you would see, whereas the top view is what the camera obtained. The bottom view is what you, the bystander, would see. And so that's this world view here is where we're getting the data from up here in the trajectory. So it's kind of neat. Now I can see, now that I've made that correction, I can see that it bounces back along at pretty much the same trajectory that it came in at, which is kind of cool. So what might we do with this now? Well, I could look for evidence of whether this is a parabola. Looks pretty parabolic to me. So yes, our model that produces a parabola is pretty good there. I could also try to evaluate whether I'm getting any sort of drag. So I could try to look at the concavity on the left and the concavity on the right and try to get an idea of whether it's significantly different there. So let's see. Let's think about it this way. So over the course of, let's just take a horizontal distance here. I'm going 1, 2, 3, 4, 5, 6 ticks to the right. I went down by 2 ticks here. So let's go over 1, 2, 3, 4, 5, 6 ticks to the left. I go down by 1, 2, 3. So I need to compare this data point here to this data point over here because that's equidistant across the peak here, right? If I go, well, let me count this one too. 1, 2, 3, 4, 5, almost 6. If I go 1, 2, 3, 4, 5, go a little bit more for almost 6. Yeah, I do see a little bit of evidence of drag because this one is at a little bit different position than this is. Not a whole lot. So there's a slight difference there that we might get from drag. Another thing that I would need to do would be to actually take into account the dimensions of the system here, right? So I need a length scale. So let's see if I can get any sort of standard item. I'm probably just going to get the length scale off the basketball because I don't know if I can get the height of the basket there. Okay, let's get our length scale set up from a basketball. So I am going to Google diameter of a basketball. Things you never thought you would have to Google. A standard NBA basketball has a diameter between 9.43 and 9.51 inches. In the WNBA, the basketball has a diameter between 9.07 and 9.23 inches. Okay, and this is at an elementary school. I'm going to guess they've got slightly smaller basketballs in an elementary school. So why don't we go to, or do they? So diameter of an elementary school basketball. This is a really dangerous rabbit hole we might end up going down for several hours here. Hands-on junior basketball, okay, is 27 inches. I really hope that's the circumference and not the diameter. Actually, yeah, that probably is the diameter. Excuse me, that is probably the circumference, because if it's 9 inches, multiply that by pi of approximately 3, you end up with 27 inches. So, all right, let's take 27 inches, divide by pi, and now let's put that in meters. So we would have a diameter of 0.218 meters. Let's call it 0.22 to be safe. So now what I'm going to do, I'm going to zoom in on the basketball here. And I'm going to attach what's called a calibration stick. The idea of a calibration stick is that I want to be able to tell the computer, I want to be able to tell Tracker how long a certain distance is. It currently thinks that that is 83 meters. Yeah, that ain't happening. So we're going to replace that with 0.22 meters. And so now what it's done is rescaled my axis here. You notice it's much smaller. It's not going up dozens of meters. So now it interprets this distance here as 0.22 meters. That's just setting the scale like you would on a map. And now what I can do is conclude that after I am done, after our basketball player here is, after our teacher here is done tossing the ball, it's gone up in our coordinate system to about 1.33 meters. Now I need to subtract off from that the lowest point here. So she tossed it from right about, let's call that 0.7 meters. So we've gone from negative 0.7 meters up to 1.3 meters. She tossed it 2 meters in the air. That seems like a lot to me. Well done, teacher there. So I know we've gone 2 meters up in the air. How far over do we go? Let's see. We go over a distance from negative 3.5 to 0.4. So we tossed it. So she tossed it about 3.9 meters over. So 3.9 meters over 1.2 meters up. So let me get out a notepad so I can record this stuff. So we went range of, how much was that? 3.9 meters. And a height of, that was right about 2 meters. So now the challenge is, can I open the Python and end up with those same results if I recreate her toss? So in order to figure that out, I would need to go to my starting velocity values. So let's go to our initial velocities here, Vy versus Vx. This is what it's doing in terms of velocity. Where is the starting point? Starting point's got to be the greatest point, right? So if I go right there at the toss, we are here at this point. So we're somewhere over here at about Vx of 7, V0x of 7 meters per second, and a V0y of about 10 meters per second. Okay, that might be a bit of an extreme value, but let's give it a try. All right, here we are back with our projectiles code. So let's try this out. Let's give our initial velocity here. We're going to go with 7 and 10. 7 and 10. The initial position doesn't really matter all that much because, oh no, wait, it does, because I want to, that does matter because I want to be able to recreate the toss from here and then it's stopping at the basketball hoop. Okay, we'll figure out how to adjust that in a second. So let's see, I need to set my gravitational field appropriately. So my gravity, we're going to make our standard Earth 9.8 newtons per kilogram. And then we're going to come over here. We'll need to change the stopping condition. So we'll need to have while the ball.pos.y is greater than or equal to, what is her final y value here? Her final y value is right about 0.8 meters. Or we want while the velocity is going up, right? So I want or while ball.velocity.y greater than 0, right? Because she's initially tossing it up, so this is going to stop whenever we go below that and whenever we go downward and when we're below that height. Okay, let's try this one out. Woo. Boop. Okay. This took 2 seconds. I traveled 13 meters in the x direction and 5 meters in the y direction. So we're a little bit off there in terms of our results. I'm wondering if that initial velocity is just a little bit too high, because 10 seems like a lot. I mean, I don't doubt this teacher's ability to throw a basketball here. Oh, do you know what? I wonder if this video is in slow motion, because the video in slow motion, that would mess up my time step there. Yeah, my velocity is all over the place up here. So I think the fact that we've got those, that lag between different frames, I think that's messing us up here. So why don't we actually try the lower of the values? Let's try a launch velocity of 4 for the y component. Because the thing is, 1 meter per second is average human walking speed. Like, you generally don't throw things a whole lot faster than you can walk. I mean, unless you're absolutely a professional, right? Professional athlete, I should say. Teachers are professionals. And let's go with the same value for x. We've got 440. My position here doesn't matter. It just matters that I'm starting at 0. And I do need to adjust that y, though. Okay, yes, I do need to make that height equal to 2 here, because I'm starting at 0. Right? I'm not starting at the same value she was. Let's click run. Okay, it took half a second, and we traveled 0.8 meters in the y direction. I was actually at her peak there. Okay, maybe I do need that. 7 and 10. 7 and 10. This is always the fun part, is you've got your data, you've got your model, getting them to match is the interesting part. Okay, yeah, no, that's definitely too much. All right, why don't we split the difference? Halfway between 7 and 4 is, let's call that 5. Halfway between 10 and 4 is, let's call that 7. But what I could do here, I could keep adjusting these until I get about the appropriate values of 4 and 2. All right, I'm getting close. I need to throw just a little bit more slowly. So let's try 4.5 and 6. And I'm just looking to get 4 and 2 here. All right, that was a little too much in the other direction. So let's try 4.75 and 6.5. Okay, I've got 4 and 2 there. I'm pretty happy with that alignment. I got 3.9 and 2, 3.99 and 2.15, so it's still tossing just a little bit fast. But I also don't have drag taken into account, so I do feel pretty confident she is tossing this with a velocity vector of about 4.75 and 6.5. Let's figure out what that magnitude is here. Print magnitude of ball dot velocity. So it looks like she is throwing this with a speed of just over 8 meters per second. So there you have it. Our model and our experiment do match up pretty well, so we have pretty good confidence that the code we've been using so far is working for us.